so difficult to say. Maybe non-specific binding, maybe something else the cause of it, but whatever it is reacting with your primary or your secondary. The signal that you see on the membrane will be reacting either with your primary, and then primary of course recognized by the secondary, then you get a signal, or you can also have a situation where your secondary reacting with your targets, right, with antigens, and then you will see them too. You will see the secondaries coming up as well. All right, and then we have our other lane there, the same idea here. Difficult to say if we see anything in this region here, kind of, sort of, but I'm talking about the second lane there. But definitely a nice signal, probably for the cell lysate, maybe for the IP, depending how you loaded it, and yeah. So if you did get a good result, as in you had either two bands lighting up or just one band lighting up, lots of things to discuss and reflect on. When you compare your SDS-PH result, okay, with the result that you get on the Western, you can see that, of course, the Western tends to be much more specific for the antigen, right? So let's just remind ourselves, our SDS-PH looked cell lysate, so many different bands, right? We had IP, which had also some bands there. We had a negative control. And then you transfer all of these proteins onto the membrane, then you blot them, and you get one signal. So Western tends to be very sensitive. When it works, it tends to pick up your target with high specificity. In the lane that you see lighting up there, lane number 9, what I marked there in red. Now, the implication, of course, is that there's all these different proteins in that lane. You saw this in the Kumasi, right? So all these different proteins, so many different proteins, and yet only one protein, which is your tubulin, lights up. So it just speaks to the power of Western. When it does work out, you can pick up that one antigen with high specificity. Westerns, of course, the extension of Western blotting, immunodetection, ELISA assays, a lot of clinical assays for antigens, viral infections, and things like that. So in the clinical setting, it becomes very important to use something that is very specific and can, in fact, pick up one antigen out of mixtures of many. So in that sense, Western does work out. Multi-step procedures, so some of you didn't get anything at all, right? So in that case, you just have to come up with a plausible explanation as to why your experiment didn't work out, okay? And a suggestion of that will suffice. So you're not required to elaborate and find the root cause of your trouble, but you can suggest, what might have been wrong. If you reflect on the experiment, so many different steps, right? You have your antibody incubating, you have your washes, you have your immunoprecipitation, of course, itself. Many of you ended up either having insufficient washes in the IP, in which case IP will be very dirty, so lots of protein there, or doing the opposite, which is actually losing a lot of proteins, washing too vigorously, right? So there's a fine balance there. But in any case, so that's as far as it goes. In your lab report, I think it would be very good if you presented your figure of your Kumasi gel, post-transfer gel, and then your membrane side by side. Okay, so in figure 1, for example, you can have 3 panels, A, B, and C, and then you can all sort of talk collectively. You can do a collective legend, and then you can talk about all of the results, because it's one experiment, even though it was over several weeks, right? So you can talk about your Kumasi, then you can talk about your post-transfer gel, then you can talk about your Western, and then you can compare them as well in terms of what was happening and what were you doing, okay? All right, now, other guidelines you will find, as always, at the end, at the conclusion of your lab. So on page 68, we have guidelines for lab report number 2. You're writing lab report number 2 in groups of 2.